But yeah, I'm so glad to be here, and thank you, Jeff, for having me step in for Rob Coffey, who wasn't able to come. So, I have a place in my heart for FRP and dual laminates because I've been involved with those for most of my career. But today I'm going to be talking about an alternative solution for corrosion protection called rotational lining. My company is R&B Products. We specialize in rotational lining and rotational molding. So what I'll be talking about today is just, what is rotational lining, the applications where you're going to see that it's a good fit, the materials that are applicable to it, and what kind of quality control steps we take to assure that it's going to be fit for service and fit for the life expectancy, and some case studies. So corrosion protection, you're hearing all about FRP and dual laminate this week. Great content and information, even some straight thermoplastic information this week. And those are great materials for corrosion protection. Sometimes, I know customers will need to use stainless steel or super duplex or Hastelloy for service environments. Sometimes you'll even use a spray coating like fusion bonded epoxy or a spray coated fluoropolymer. Kind of where my company fits and this technology is going to be on the lined steel. And there can be slip liners like PTFE liners, sheet lined like PFA, wallpaper where you've got welded seams, and then a bonded liner. And that's where rotational lining fits. These are some photos of rotational lined equipment. So it's always going to be a steel substrate. And whatever the configuration is, if it's a pipe, a vessel, any component, whatever pressure rating, that liner is just going to conform to the inside of it and provide that corrosion protection. So kind of going back to what is rotolining, it starts kind of earlier back from there, which is rotational molding. And rotational molding is used all the time around the world to make everyday components like trash cans and kayaks and coolers. It's where there's a cavity and granular resin is poured inside. It's rotated, and that resin conforms to the whole inside of that mold, making a one-part piece, kind of those examples that you see there. There are more sophisticated rotational molding applications like aerospace ducting, pharmaceutical containers, and high purity containers as well. This would be an example of a machine doing rotational molding. It's got the two different directions of rotation. And in this case, there are two molds there so that the machine is balanced. And when this is finished, those two parts will be unclasped and you'll get two identical rotational molded parts. What we do differently here is that we want that resin to stick. So there are certain steps that are going to be taken so that when that resin is poured into the cavity, that it bonds to the prepared metal. So we count on that mechanical bonding to provide that corrosion resistance inside the metal part. And we start with the thermal degrease or burnout, and then we will grip blast the interior with the appropriate blasting media, and then we clean it by vacuuming it and putting an IPA rinse. I'm going to go into more detail about how the rotational lining process works, but basically the difference is we want that resin to stick. It's very important that it adheres as a bonded liner. So just taking an elbow, for instance, we're going to blast the inside surface, including onto the face, to the SSPC SP5 white metal. And this rough surface is going to be about a 3 to 5 mil depth surface profile. What this does is that when the resin is then inserted and bonded, we get a vacuum rating. We actually have that strong of a mechanical bond with many of the resins that it can be a full vacuum rated part. And there's no annular space whatsoever between the resin and the steel. Once we've done the surface blast, we put the resin in, it's in granular form, powder form. We close it up, we put it on an arm and put it into the oven, into the temperature that's going to melt that resin. And as that part rotates, that resin flows and covers all of the internal surfaces, including onto the flange faces where there would be wetted surface. So once we're done, take the covers off We've put rings onto all of the flange faces so that we can get some liner onto the flange face, and it looks rough there, but we do clean it up with the machining process. This is the point where we're going to inspect the liner, make sure that visually it looks good, and I'll get into more detail about what other quality control we do. Finally, we do a machine process onto the face where we make sure that it's true and flat to the specified tolerance. So there you go. So that would be a fitting. Now, in the case of a vessel, much more heavy, there's going to be more rigging. You can see this vessel rigged up onto this arm here. And in fact, I have a little video here which shows what we do. In this case, this vessel has been preheated. So it's already hot. It's so massive that we need to make sure it's already got some of the temperature going. So we are very quickly going to be dropping the resin into the opening there using this hopper. And in this case, it's ETFE or Tefsel resin in granular form. And we pull it over, and it's just the right amount to get the thickness of liner that we're looking for. And we very quickly will pour that into the vessel. Once we're done, we close it back up. It begins to rotate and gets right back into the oven for its heat process. So following the heat process is a very controlled cooling cycle. The cooling cycle is the most important part because we have to make sure that no stresses are imparted into that thermoplastic liner. So it's a very gradual cooling process to make sure it's not going to crack or contract very quickly. So there are many aspects to consider on whether or not something's a candidate for rotational lining. The part geometry, actually, the more complicated it is, the better candidate it is. But we do need to make sure that we can get to all the areas inside to get a consistent liner. There are some products that we have to turn back just because we cannot get them rotolined adequately. For instance, if the nozzles are very small, like 1-inch diameter, sometimes if there's a jacket, then it's difficult to get the heat to the inside where we need it to get a good consistent heat transfer. Sometimes there are differentials in mass where we can get different temperatures of the part because there's a heat sink, and we will get different thicknesses of the liner. So just several things to consider when we go to design the process for unique parts. The part size, we typically don't like to go below 1.5 inch. And in terms of the large size, it just has to be able to fit in the ovens of a given supplier. Key customer inputs that we're going to need are if there are any areas where you have a clearance issue and you're going to need for something to fit in, then we may need to do a machining process on the liner to make sure that clearance is there, or maybe upsize a nozzle dimension. A lot of times we have some very savvy customers who are very used to using rotational lining, and they're going to have source inspection. And they know exactly what they want, and we have to do certain quality control checks through an ITP routinely through the process. Others, they just want to see the finished good. So that's something we want to know at the very time that we're quoting, what is your level of inspection? And then finally, we can do an external coating, so it's important that the outside is corrosion resistant. A lot of times, many customers have their own specification for that. Some of the important features of the metal for it to be rotational lineable are that there are no sharp corners. So the resin's not going to flow well over sharp corners. So it has to be prepared so that any internal and external radii are about a 3/16 minimum curvature. For slip-on flanges, we're going to need to make sure they're welded so that there's no crevice both on the inside and the outside. Root welds need to be ground smooth. So basically, we just can't have anything that's going to cause any flaws in the liner. We're going to pick up on those flaws in the metal with the liner. And specifically for porosity, that can cause bubbles in the rotational lining process. So the metal condition is very, very important. I can speak to the kind of machines we have, but we also have what is on the market generally. So for even other rotational liners, the limits are going to be 20 foot long by about 6 foot diameter. And then for large vessels, 12 foot high by 10 foot diameter. Typically, that's the window that the current machines provide for rotational lined equipment. Diameters as small as 1 inch. When we get a request for quotation, we will make sure that the equipment is going to fit in our machine by modeling it in SolidWorks to make sure it's going to rotate in both directions and not hit the wall of the oven. Kind of to give you an image, this is what the larger machine it looks like. That's the door closed. The inside is where the convection oven is. This machine is called a rock and roll machine. Also, other rotoliners are going to have this kind of machine for 20-foot lengths. Rotates on the axis, and then it goes up and down into the ground 45 degrees to get the two directions of rotation. So you could imagine that there are many applications in chemical processing for rotational lining. Anything that's got a cavity inside that can be closed off can be rotationally lined. Tanks, columns, duct, pumps, valves, piping, reducing flanges, strainers, dip tubes, heads, flow meters. Virtually anything that can be closed off can be rotationally lined if it's metal. There are some secondary operations that are sometimes necessary, like if there are baffles that are needed, they can be welded inside with a plastic technician, welding technician. Machining can take place after the fact as well. So the materials that are typically used for rotational lining are ones that are available in rotational lining versions. So there are some resins that are more suitable and some that aren't. These are the ones that work well for rotational lining because they stick. Well, in the case of the bottom three. So, excuse me. HDPE, Kynar, and Tefcel all are going to bond very, very well to the metal. And they actually offer versions that are good for rotational lining. Now, in the case of PFA Teflon, it does not stick well, and a primer is necessary to make sure that it adheres to the metal. But sometimes PFA or Teflon is the only choice for some applications because of the high temperature. Just kind of to dig into those resins a little bit more, on the HDPE side of things, we're going to see about up to 180 degree limit in temperature. It's great for weak acids, brine, seawater. It's good for erosion, for slurries. It can be provided in black or natural. This bonds very, very well. Full vacuum is provided. Typically, we're going to line this to about 320 thousandths thick. It can be lined as much as a ½ inch thick, though. And it can be provided with an anti-mic or anti-biofouling additive in case you have any problems with that. It is permeable to hydrocarbons. So there's going to be a limitation, and it's just a really good kind of everyday resin. We use it a lot for oil and gas for brine applications. Then the next step up is going to be ETFE or Tefcel. This is going to be good up to 302 degrees Fahrenheit for most chemicals. It does get derated for some more aggressive services. This is kind of the workhorse in rotational lining. I know that you don't hear of Tefcel or ETFE that much for like tubing or for sheet lining, but it's a great resin because of its bond strength to the metal. So it's got good abrasion resistance. It's very impact resistant. So it's just an excellent choice of a resin for this kind of application. Now, it also has lower permeability to PTFE or than PTFE. But if the temperature exceeds 302 or if the service environment requires it, the next step is going to be PFA. This is pretty much inert to all chemical streams. So this is going to be lined to about a 3/16, and it's going to be a two-part process with a primer and a top coat. It's limited, though, in size because once the sizes get above 24-inch diameter, it can tend to delaminate. So we have learned over the years just to limit this to 24-inch diameter and 100 inches long. These are some kind of nightmare pictures, but this is where upset conditions kind of took over, or maybe the wrong resin was used. Where rotolining can be problematic is going to be when there's a lot of thermal cycling. And as you know, we heat it up to the temperature that it's melting, we apply it to the part, and we cool it down slowly. Now, when it is in a hot service environment, that's okay because that's its natural state. But if it sees a lot of fast cooling, it's going to want to contract faster than the steel. And that's where we see some problems. So when we talk to customers about applications, we like to know what kind of thermal cycling, what kind of cleaning process, if there's going to be a steam sparge, and those kind of sort of non-standard operating conditions. These are all very, very important. Sometimes, you want 20 years out of equipment. Sometimes if you can get 2 years, you're happy. So we do actually also like to know the life expectancy. For quality control, we do have a CMM measurement. Sometimes there are some very critical dimensions that we need to double check. We do ultrasonic thickness reading. We do spark testing. Sometimes we have to borescope to see inside and make sure that visually there are no bubbles and flaws. We can do hydro testing. We can do that to the metal before, and we can also hydro test after it's been lined. The adhesion testing, which is this ASTM D3167, is a method to determine what the strength of the bond is. So this is how we're able to stand behind our vacuum rating, by knowing what the strength of the thermoplastic is to the given metal substrate. And there is a standard for lined pipe. It's ASTM F1545. Section 6 of this standard provides these different tests: high temperature, low temperature, vacuum, and steam cold. These are kind of long-term tests, very expensive, but they're something that we subscribe to when we're trying to qualify a new product, a new combination of resin with metal. So some case histories. This is actually the tank that I showed rotating earlier on. It was 10-foot diameter, ASME Section 8 code, 35,000 gallon. And this was an ETFE lined, 3/16 thick liner, done in 8 weeks. In this case, there was this impact floor protection made of PTFE in the bottom. So that is an example of what the cooling cycle looks like. Another example, this is for CNRL, supplied these 52-inch diameter elbows. And at first, we did not even know if these were going to be something we could do because they were so large. And we came up with a mounting fixture to be able to rotoline them. And we're able to take that project on. So that was an oil and gas application. Also, quite a bit of work goes into offshore platforms using the BioArmor, which is the HDPE with anti-mic. And in this case, this was these caissons, as well as quite a bit of HDPE line piping with an exterior top coat. These were a number of spools supplied to a VCM plant. In this case, this company trialed the ETFE lining for 5 years, and their PTFE started to bulge and fail. And they noticed that the ETFE looked like brand new, so they replaced everything with the ETFE rotolined equipment. They needed 90 spools in 10 weeks, so that was quite an achievement. And it actually saved them money over what the PTFE would have been to replace it in kind. And this is one of those that doesn't last 20 years. It's a quartz tumbler. It's very abrasive. It's got an acid media in it. And they were getting 3 to 6 months using a PTFE liner. And they found out about ETFE rotolining and are now just standardizing on that approach. So they're getting 2 years, 3 years, still not a full 20 years, but better than anything else they could find on the market to stay up and running. As this is one of the more aggressive services that rotolining would be serving. And just some examples of some various rotolining applications, like the bonnets for heat exchangers, a cross that's been fabricated and lined. Instrumentation tees is a great application for rotolining, and just various pipe spools. So just to give you kind of an image of where this applies. And that concludes the presentation.